Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Classical general relativity, despite its profound successes in describing gravity, falters dramatically when confronted by the universe's earliest moments. The theory predicts an initial singularity, a point of infinite density and space-time curvature where the very laws of physics, as we comprehend them, break down. This singularity presents cosmology with a formidable problem: how can we understand the origin of the universe if our best theory ceases to function precisely when and where that understanding is needed? Stephen Hawking offered one of the most audacious and influential attempts to resolve this quandary through quantum cosmology, most notably with his no-boundary proposal, also known as the Hartle-Hawking state, presented in the seminal 1982 paper. The proposal constitutes a radical departure from conventional cosmological thinking. Its primary thrust involves replacing the singular boundary condition of the universe with a regular, Euclidean spacetime region, successfully eliminating the troublesome initial singularity. The genius of Hawking's approach lies in its application of quantum mechanics to the universe as a whole. The no-boundary proposal does so by utilizing the concept of imaginary time. Imaginary time offers a mathematical tool to smooth out the initial singularity. It involves analytically continuing the metric, a mathematical object describing the geometry of spacetime, into the complex plane. Effectively, this process transforms the Lorentzian spacetime of classical general relativity, characterized by a clear distinction between space and time, into a Euclidean spacetime, where time behaves as another spatial dimension. This analytical continuation into imaginary time allows for the consideration of a universe which is spatially closed and has area zero. This zero area is the south pole on a sphere. There is nothing south of the south pole, so there is no boundary. Therefore, a solution is provided to the boundary conditions of the universe. The mathematical framework for calculating probabilities in quantum mechanics is the Feynman path integral. The no-boundary proposal states that one should perform a sum over all possible compact Euclidean 4 geometries. Each geometry is weighted by an exponential factor involving its action. This exponential factor is analogous to the exponential weighting factor encountered in statistical mechanics. Through this sum, one calculates the function of the universe and the mathematical entity encoding the probability amplitude for finding the universe in a particular. The no-boundary proposal claims the universe arises from nothing without any prior boundary or singularity. Nothing in this context refers to the absence of classical spacetime. This radical assertion immediately sparked fierce debate and diverse interpretations within the physics community. The notion of a universe spontaneously emerging from a state devoid of spacetime structure challenged deeply held intuitions about causality and initial conditions. The philosophical implications of the no-boundary proposal are immense. It addresses the fundamental questions concerning the origin of the universe and the role of initial conditions in determining its subsequent evolution. If the universe has no boundary, then it requires no external cause or pre-existing state to initiate its existence. It becomes self-contained and self-creating, sidestepping the need for a prime mover or an external agent. Hawking's work was deeply rooted in the intellectual landscape of his time. He directly drew from Feynman's path integral formulation of quantum mechanics, adapting this powerful technique to the realm of gravity. He also built upon the pioneering work of Bryce DeWitt on quantum gravity, exploring the application of quantum field theory to curved spacetime. Further, Hawking's own groundbreaking research on black hole thermodynamics, particularly his discovery of Hawking radiation, provided crucial insights into the interplay between gravity, quantum mechanics, and thermodynamics. The influence of Roger Penrose on Hawking's earlier work on singularities similarly shaped his later approach to cosmology, seeking to resolve the singularity problem through quantum mechanics. The initial reception of the no-boundary proposal was met with both excitement and skepticism. Some physicists saw it as a brilliant and elegant solution to the problem of the initial singularity, offering a consistent quantum mechanical picture of the universe's birth. Others expressed concerns about the mathematical ambiguities and interpretational challenges associated with the Euclidean path integral, as well as the philosophical implications of a universe without a cause. The radical nature of the proposal, challenging fundamental ideas about causality and the role of initial conditions, naturally provoked scrutiny and did. Hawking's 1982 paper, Quantum Cosmology, hinges on the no-boundary proposal, suggesting the universe possesses a finite size, Euclidean 4 geometry with topology of a 4-sphere, and no boundary at the beginning of time. The wave function of the universe, a central object of study, receives definition through Euclidean path integral over all compact 4 geometries, whose only boundary is the 3 geometry on which the wave function is defined. This approach, avoiding an initial singularity dramatically alters the standard cosmological framework. Delving into the technical aspects, the Euclidean path integral, a sum over all possible geometries connecting an initial and final state, becomes central to evaluating the wave function. This involves Wick rotating time to imaginary values, transforming Lorentzian spacetime into a Euclidean space. The path integral takes the form of an integral over all metrics and matter fields that satisfy the boundary conditions. However, immense challenges arise. The space of four geometries possesses infinite dimensions, making the path integral extremely difficult to define rigorously. Issues like choosing a suitable measure, a weighting factor for each geometry, loom large. Convergence of the integral presents another hurdle. As the action is unbounded below, one tackles these through various regularization techniques, a delicate process fraught with ambiguities. To extract physical predictions, one frequently resorts to the saddle point approximation, also known as the method of steepest descent. This approximation identifies the dominant contributions to the path integral from geometries close to stationary points of the action. These stationary points correspond to classical solutions of the Euclidean Einstein equations. One then expands the action around these saddle points, performing Gaussian integrals to obtain an approximate expression for the wave function. The saddle point approximation offers a valuable, manageable approach to sidestepping the full complexity of the path integral. One of the most striking predictions arising from the no-boundary proposal involves the spectrum of primordial density fluctuations. These fluctuations, tiny variations in the density of the early universe, served as the seeds for all the structure we observe today, from galaxies to galaxy clusters. The no-boundary proposal predicts a nearly scale-variant spectrum of these fluctuations, characterized by a power law with a spectral index close to 1. This prediction aligns remarkably well with observations of the cosmic microwave background, the afterglow of the Big Bang, as measured by experiments like WMAP and Planck. The CMB anisotropies, tiny temperature variations across the sky, directly reflect the primordial density fluctuations. Determining the precise spectral index and the amplitude of the fluctuations remains a key test for models of the early universe. Despite its success, the no-boundary proposal faces criticisms and alternative interpretations. One prominent alternative involves the tunneling from nothing scenario championed by Alexander Vilenkin. In this scenario, the universe originates from a quantum tunneling event, creating a de Sitter space from a state of literally nothing. While differing in its initial setup, the tunneling scenario similarly predicts inflation and a nearly scale-variant spectrum of density fluctuations. The interpretation of the wave function of the universe also continues to ignite debate. Is it a probability amplitude for the universe to exist with certain properties, or does it require a more exotic interpretation, perhaps involving multiple universes? The 1982 Quantum Cosmology paper exerted enormous influence on subsequent developments in quantum cosmology. It inspired a vast amount of research into the quantum origin of the universe, stimulating the development of inflationary cosmology and the multiverse hypothesis. Inflation, a period of accelerated expansion in the very early universe, offers a compelling explanation for the flatness and homogeneity of the observable universe, resolving many puzzles of the standard Big Bang model. The multiverse hypothesis, springing from eternal inflation, posits the existence of a multitude of universes, each with its own physical laws and constants. The no-boundary proposal, serving as a potential mechanism for initiating inflation, provided a theoretical foundation for these The enduring legacy of Hawking's quantum cosmology lies in its capacity to ignite profound philosophical implications and research into the quantum origin of the universe. It pushed the boundaries of theoretical physics, grappling with questions previously relegated to metaphysics. The no-boundary proposal still serves as a subject of active research and debate. It continues to exert influence on contemporary cosmology and theoretical physics. The influence of James Hartle on Hawking's approach to quantum cosmology cannot be understated. Their collaboration led to the formulation of the Hartle-Hawking state, a specific realization of the no-boundary proposal. As for subsequent work, Alexander Vilenkin's tunneling proposal offers a notable alternative, further enriching the landscape of quantum cosmology.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.